Geography of Soils, Final Exam. Chapter 5 is Soil Forming Factors. Soils as a component of the ecosystem. So 5 soil forming factors are climate, organism, relief/topography, parent material, and time. Climate is considered the most important. On the long run, climate is the most important factor. What are the 2 characteristics that make up climate the most? High temperature and more precipitation. High temperature is helps chemical reactions run faster. More precipitation means more transportation of materials into the A horizon from into A horizon from E to B horizon out of the soil. Also, precipitation helps with weathering and more erosion. This is due to leaching. Characteristics of low and high precipitation. In low precipitation, salt content is high, pH is high, wind flow influx is high, clay content is low, and CO3 content is high. This is all due to leaching. As you see, with high precipitation, salt content is low because it's dissolved and leached out. The pH is low because cations are leached out. The wind flow influx is low. Wind flow influx is the sediment brought in by wind, and usually with high precipitation it would be moved because of weathering. And then clay content is high because of the more weathering giving a more fine material, and the CO3 content is low because it's dissolved/leached out. For organic matter as a function of climate, in dry areas organic matter is low because of the low input, which means there's not a lot of organic matter. With wet areas, organic matter is high, but has a low decomposition rate. Like swamplands, organic matter kind of just sits in the wet area because there isn't a lot of acid because of the lack of oxygen, which is an anaerobic area. Moist/warm, the organic material is low with a high decomposition rate. And moist/cold is the opposite, with organic matter being high but a low decomposition rate. Quick recap: wetlands in tropics, organic matter content is high. Wetlands in Alaska, organic content is high. Large-scale influence of climate on relative soil depth and clay content. So, at the equator, 0 degrees, soil thickness is thick and weathered, and clay content is high. At 30 degrees, it's thin, too dry. The soil thickness is thin, too dry, and the clay content is low. At 60 degrees, the soil thickness is intermediate and the clay content is intermediate. And at 90 degrees, the pole, the soil thickness is thin, too cold, and clay content is low. Organic carbon in soils. 80% of terrestrial sea is in soils. There is 3 times more carbon in soils than in the atmosphere. Soil forming factors with topography. 3 attributes of topography that affect soil formation is elevation, aspect, and slope. Elevation is the indirect effect of temperature on a large scale and depth to the groundwater table on a local scale. Aspect is the direction that a slope faces. So if the aspect is facing north, it will be cooler and moister, while the aspect is facing south will be warmer and drier, and rinse and repeat for north and south aspect all the way through. This is in the northern hemisphere. For slope position and gradient, at the summit there's a little erosion, and shoulder slope is the most erosion, and back slope has a little erosion, and foot slope and toe slope has deposition. So in total for slope there is summit, shoulder, back, foot, and toe. Soil forming factors with topography. So here are some examples. So in Virginia, a south and north aspect, rocks weathered in place. Soils in weathered sandstone, south plus north aspect. Soils in weathered genus, south plus north aspect. Minor differences in soil characteristics between north and south aspect. Less mineral diversity, mostly quartz. compared to the north aspect. South aspect is thicker soils, more clay, and more iron oxides. In North Florida, upland wetland transit, a cross-section has coarse sands, and at the summit in a North Florida example, the clay content would be less than the toe. The organic carbon would be less than the toe. pH would be 5, while the toe would be lower, more acidic, 3 to 4, and CEC would be lower in the summit than the toe slope. And erosion at the summit is, erosion says deposition at the summit is neither, while deposition is at the toe slope, because the materials, like said earlier, all stack up there because the erosion brings it down. In a marine terrace on the coastal plain in Florida, the Fe3 content would be less to the summit and more on a shoulder. Colors for the summit would be not as red because of the less iron content, the Fe3, and more reddish in the Y. And then the E horizon would be thinner at the summit and thicker at the Y, while the B horizon would be weaker / less at the X and more at the Y. And the reason for the lesser B at the summit is because the materials would be going down with erosion, causing not as much leaching to bring metal ions into the B horizon to cause the clay to form. Soil forming factors for organisms. So soil forming factors for organisms is like a love triangle. The climate affects the soils, the vegetation is affected by soils, and it's rinse and repeat for everything. Climate affects vegetation, and vegetation affects climate. Soils affect vegetation, and vegetation affects soils. What we'll be focusing on is the vegetation and soils. In a forest prairie, with forest versus prairie boundaries in the U.S., a prairie has a thicker A horizon because it has a lot of organic material, and it has a B/BT horizon and a C horizon, while forest has a thin A horizon and E horizon, a B or BS or BH, BS for warm, BH for cool, and a C horizon. An E horizon under the forest, because the upper parts of the soil are more acidic under some forest. The clay particles are more dispersed because of more alluviation, more E horizon development. The different type of organic acids, forests have fulvic acids, low molecular weight, and more soluble, better chelating agents, more alluviation such chelation with a more E horizon. Grass has humic acid, higher molecular weight, less soluble, less alluviation, less E. This is due to the organic material found in forest and prairies. Prairies have a higher turnover rate, causing more organic material versus forests, because prairies are made up of grasslands, and a majority of the grasslands are found in the soil with the roots, and they die faster than in a forest, which trees last longer and the roots aren't as spread out. So it's a less of a turnover rate. Effects of individual plants on soils. So the effects depend on the species. So like a beech funnel shaped tree with smooth bark causes stem flow because it's in the shape of a funnel. It causes less organic material, less nitrogen, a lower pH, and lower clay. Which a fir tree, which is more angular at the top, causing the drip line to go further out, has rougher bark, causes the cations to be leached. And a Kuru pine in New Zealand, it has very acidic litter, big and long-lived. The O horizon thick because of slow decomposition. And on a side profile, the O horizon goes further up under the tree than around it, and an E and BH horizon forms under the tree, while on the outside there's just O, A, and BT. It creates an egg shape, a cup podzol, under the tree. Animals' effect on soils. Many earthworms. Animals have many effects because there's many different animals which do different things. In soil, there's about 1 ton of earthworms in a pasture soil, which is 1 ton per 1 HA, which 1 HA equals 2.5 acres. The effects of animals on soils: decomposition of organic materials from microorganisms, pedoturbanization, which is the mixing of soils from macroorganisms, and layering of material. For example, in an area before termites, rock fragments, sand, silt, and clay are all mixed, while once termites are introduced, the finer soils like silt and clay are more layered at the top, while the rock fragments and sand go towards the bottom. Additional organism that affects clay is humans. Humans are probably the most important one, as we do the most damage to it. From tilling, pollution, we cause erosion, we remove soil, we cover soil. Parent materials effect on soils. So the 4 things that parent material will make up is mineralogy, texture, CEC/fertility, and color. Mineralogy is the parent material's only source of mineral, directly or indirectly. No quartz in parent material, no quartz in soil. For example, texture, hard mineral equals a soil sandy, soft mineral equals a soil clay. CEC fertility is the amount and type of clay mineral, depends on the mineral and parent material. And the color, parent material rich in iron is reddish, parent material no iron, no red. Soil forming factors in parent material. In mineralogy, parent material's only source of minerals is directly or indirectly. Texture, hard minerals, soil sandy, soft minerals, soil clayey. CEC fertility, amount and type of clay depends on minerals in parent material. Color, parent material rich in Fe, parent material no Fe. Are we currently in an ice age? The answer is yes. We're in an interglacial ice age period. So ice age equals glacial plus interglacial periods. So these are examples. Just like the ice age was one of the examples. Mississippi Valley is another example. Because the Mississippi Valley is cold, dry, little vegetation, last glacial X section. With wind erosion, the wind moves from west to east, causing layers to develop differently from the silt. An A layer has the thickest and the horizons are A, B, W, C, and it's less developed because the A horizon gets most of the deposition before it moves down. The B horizon is the next thickest, and it has an A, B, T, and C horizon. The C horizon, no, this isn't right. No, the C section is less thick than the B, and it has a thick A horizon, a BT horizon high in clay, and a C horizon, and D, which is all the way at the end of the deposition, has a thick A, and E, a BT high in clay, and C. This is where the soil's most developed because it's had the longest time. In the New York State, coarse sand becomes finer clay because it goes from arid to alkaline. Sandstone, Calar sandstone, sandy limestone, and limestone over the distance. So sandstone has a very little A horizon. Same with Callar sandstone, sandy limestone. Oh, no. So sandstone has an A horizon, an E horizon, a BW, and a C. The A horizon is very little. The clay in the E horizon, very low BW horizon, and soft mineral C. At the end in limestone, the A, E, BW, and C, the clay does not move down, causing BW, which means a weak B horizon. Diffuse double layer theory. So in an acid E horizon, the clay wall has a thick outer layer and it is more dispersed and moves around because the metal ions, because of leaching, goes down to a more arid B horizon. And let me pull up a picture to explain this better. So an E acid horizon, the water moves down. Leaching causes the complex metal ions, the Fe3+, the AE3+, and Ca2+, to go down to the B neutral horizon, while H+ ions stay in the more acidic E horizon. And because the clay is negatively charged, it has multiple negative charges, and each of the H+ ions connect to a negative charge, causing a larger wall to develop around the clay, while in the B neutral horizon, because it has more complex metal ions like Fe3+, which take up multiple negative ions in the clay, causing a thinner wall, which also can cause the clay particles to stick together because the complex metal ions, the 3+ or AE3+ or Ca2+, can connect to other clay particles, negative ion charges. So a B neutral has a thin outer layer and the clay remains fluctuated and it does not move. It sticks together versus an E horizon where it's more dispersed and moves around. Time's effect on soil. Over time, a soil may continue to develop, get older, get buried, frozen in time, erode, and become parent material for a new soil. So time zero. Time zero is a catastrophic / cataclysmic event. Stuff like lava flow, retreat of glaciers, landslide, recession of sea, strip mining, explosion, tsunamis, and meteor impacts are all catastrophic time zero events. So recap. So time as a soil forming factor. Time zero is a cataclysmic event. Then after the cataclysmic event, soil continues to develop, get buried, erode, and become parent material. The evolution of A horizon over time. Organic material in A horizon builds up faster than any other material in a soil. It's a simple process and it's a fast process. And the A horizon takes 100 to 1,000 years to fully develop. The buildup of organic material and development of an A horizon is very fast and then slowly slows down. So it's fast at first and then slows down. The evolution of a BW and a BT and a BK horizon. The BW takes 1,000 to 10,000 years. A BT BK takes 10,000 to 100,000 years. And BT is weathering, translocation, and it's slow. So how does BT horizon change over time? The BT horizon clay content increases thickness and increases and it gets deeper, causing deeper, thicker, and more clay in the BT horizon. So a recap on the horizon development. A horizon takes 100 to 1,000 years. BW the W stands for a week, so it's a week B horizon, is 1,000 to 10,000 years. BT and BK horizon, 10,000 to 100,000 years. And a BO horizon is anything takes greater than 100,000 years. A BO horizon has to have lots of weathering, leaching, and a lot of time. The soil formation is slow. Over time, horizons get thicker and more developed. More organic material in A, more clay in BT, more calcium carbonate in BK. So a recap on the soil forming factors. You got climate, which is the most important, organisms, topography, parent material, and time. So for age dating of soils, to continue on with time, there's two types of age dating. There's relative, which is older than, younger than, which is basically comparing. So you compare one object to another. And then there's absolute age dating, which is a numeric. So you're going to get like a number. So example would be like 75,000 years. Relative age dating methods are soil-based methods, uses soil characteristics and assume other soil functions are constant. Surface exposure dating methods determines age of surface, not the age of soil. Assumes soil is as old as the surface. Soil-based methods include leaching depth of CaCO3. The deeper, the older the soil. Solemn thickness, which is basically horizon thickness, is horizons above sea horizon. The thicker, the older the soil. So anything over like the sea horizon is solemn. So your A, your E, and your B, and anything that, other variants of that. The color related to the organic material and iron content, darker or redder soils is older. Other soil characteristics that can be measured is texture, particle size. It gets finer with age because there's more time for weathering. Clay content increases over time because there's more time for leaching. The leaching of other elements increase with time because there's more time for precipitation to cause leaching. Organic material content increases with time because there's more time for plants to grow and die and repeat that process. The depth to the BT horizon increases with time, and the only thing that doesn't increase is the pH. pH decreases with time because the cations have more time to be leached out. A ratio to measure the soil-based method is percent resistant material divided by percent weathered minerals. So resistant minerals are minerals that, thicker, they don't weather, while the weathered materials are the more thin, they've been weathered. So main points of this is horizons build up fast at first, then more slowly. It's a steady state. And make sure to remember how long each horizon takes to completely develop. Your A horizon takes 100 to 1,000. Your B horizon takes, let me just make sure I'm getting the horizons right, because I remember the numbers. I just want to make sure the horizons are correct. Yeah, your A horizon is 100 to 1,000 years. Your BW horizon is 1,000 to 10,000 years. Your BT and BK horizons are 10,000 to 100,000 years, and your BO horizon is 100,000 years. Anything greater than 100,000 years. And then make sure to remember examples of relative age dating and absolute age dating. So another example of relative age dating is surface exposure dating methods. Weathering rinds. This is discolored layers, rinds on outside of rocks, thickens with time. An absolute age dating method example is the most common is the 14C method. So dates organic material in the soil. So there is 3C isotopes, and a 12C is stable at 98.9%, 13C is stable 1.1%, and 14C is unstable 10 negative 12%. This undergoes radioactive decay. In the 12C, there is 6 neutrons plus 6 protons. 13C is 7 neutrons plus 6 protons. And 14C is 8 neutrons plus 6 protons. There will always be 6 protons, and then it's just equal to what is the number above the C. C is carbon, obviously. So for this, you need to know the initial ratio, which is 14C divided by 12C. Know the rate of change of the ratio, the rate of decay of the 14C. The measure current ratio of 14C divided by 12C in soils and organic material, and can calculate time 14C has been decaying in organic material. The 3 limitations of 14C dating for soils is it gets an average of organic material, the age of organic the age of the organic material is a minimum age of soil, and the method is reliable up to 50,000 years for any material. Lycometry is another example of absolute age dating. Lichen is the fungus plus algae that grows on trees. The diameter of the thallus is proportional to the age of lichen. It's best used for less than 1,000 years, so a minimum age. Now, back to 14C age dating. So for the initial ratio, it's 5,730 years equals time and a half, which is the half-life. So a very simplified example, initial ratio starts with your 14C divided by 12C, which is equal to about 10 over 100. The decay rate is 1 per year. So measure the ratio more than 6 over 10, 6 divided by 10. It's 4 years, because it takes 4 years, because the decay rate is 1 per year, for 10 to get to 6. So 10 minus 6 is 4. And that gives you your decay rate. And then back to other examples of absolute age dating is dendrochronology. It's best for young soils, and it only is a minimum age. So now that we're over with time, we go over wetland delineation and hydric soils, which hydric soils just mean wetland soils. So important factors is vegetation or hydrophytes. In an upland, it is 99% in upland. A fallow-silitive upland is 67 to 99% in upland. Well, fallow-silitive upland. Fallow-silitive itself is 33 to 67% in upland. Fallow-silitive wetland is 67 to 99% in wetlands, and obligate wetland is 99% in wetlands. Hydrology is another example for finding evidence of wetlands. It is evidence for ponding of high water tables, so water buildup in the soils. And then soil evidence for saturation. Hydric soils, wetland soils, formed under conditions of saturation of flooding long enough to develop anaerobic conditions. Anaerobic is the lack of oxygen. Hydric soil field indicators depend on region and texture, muck/peat. And hydric soils formed under conditions of saturation of flooding long enough to develop anaerobic conditions. Hydric soils field indicators depend on region and texture, muck/peat, which muck is like organic material. Organic material, rich surface, presence of H2S, which is a bad smell, within 30 centimeters of the top. Stratified layers starting up in the top 15 centimeters, and less than 60% glee within the top 30 centimeters. Glee is reducing gray, and then redox features, so the reduction of oxidation, and then oxidized rhizophyres, pore linings in in the soil. So some terms that are supposed to be known for the test is element, which element, according to Google definitions, is a pure substance consisting only of atoms with the same number of protons in their nuclei. Another term is atom, the basic unit of a chemical element. Ion, an atom or molecule within a net electric charge due to the loss/gain of electrons. Molecule, a group of atoms bonded together. Mineral, a naturally occurring inorganic element or compound. Nutrient, a substance that provides nourishment essential for growth and maintenance of life. Leaching, drain away from soil, ash, or similar material by the action of liquid. And then horizons, a layer parallel to the soil surface whose physical, chemical, and biological characteristics differ. Now the final thing to go over is soil taxonomy. So this is soil classification, which also is soil taxonomy. So soil taxonomy is the order, the suborder, the great group, the subgroup, family, and series. The reason for classifying soils is mapping, tax, inventory, management, and use. There are 12 orders. Gillisols, which is frozen, histosols, which is organic material, wetland, spodzosols, podzol, EBH, andisols, volcanic ash, oxasoils, BO, vertisoils, invert mixing, iridosoils, arid dry, aldosoils, ultimate, highly weathered, lots of clay, mollisoils, lots of OM, prairie soils, soft, alpha soils, forest soils, inceptisoils, inceptant, and then entasoils, which is all other soils. Nomenclature are the below level of order. Name of suborder is one syllable plus formative element, which is the order name. Name of a greater group is one syllable plus name of a suborder. Name of suborder, add one or two words to the name of great groups. Family name, add 3 words to the name of suborder. Word describing texture, mineralogy, and temperature. Series name is the local name. So order equals formative element, suborder equals add syllable, great group add a syllable, suborder add 2 words, family add 3 words, and series is the local name. Soil series and their family names. Troposoils, lumicalonic, thermic, brossiferic candidates. Lakeland series, thermic coated, typic quartzimenses. Let me pull up a better, because my handwriting's not as good on this one for reading, and I'm not even sure I'm getting the names right anyways. So malic soils is fine mixed, subactive, thermic, aquic, haplodotes. Dorigo series is sandy or sandy skeptical, cilios, euic, thermic, terric, sulfurous. Coton series is lumi, silicious, disic, thermic, terric, hapalus, suppressed. Ascambia series are coarse, lumi, silicious, semi-active, thermic, plantopheric, palidotes. So for this, it's more just remembering just how to find it. He's going to give the sheet with all the names and series on it, and from what he described in class, you're going to just have to describe the soil. He's going to give you a name, or he could give you, a description. You have to name it. So remembering more of The order is the formative element. Suborder is the added syllable. The great group is another added syllable. Subgroup, add 2 words. Family, add 3 words. Series and equals the local name, which is the, like the area, like Escambia or something. But an example of the naming, so he gives lumi, salacious, thermic, grosseric, plinthic, paludate soil. So lumi is just lumi, and then salacious is silica, thermic means warm, gross is thick, and arenic is sand. Plinthic is plinthite, pale is old, oud is humic, and alt is ulta soils. Best of luck. You got this.